In this video, we present Shift, a synthetic drawing dataset for continuous multitask domain adaptation. In the past decade, dataset has been one of the most powerful driving force for autonomous driving. Endless hours of human annotation and billions of dollars budget have been devoted to such efforts across academia and industry. However, it is still utmost important for driving datasets to capture all conditions to prevent unseen environments leading to life-threatening outcomes. While the real world is diverse and continuously mutating, we believe that the ideal driving dataset should lay its foundation on three pillars: annotations for multiple tasks in a single dataset, diversity of conditions, and a continuous shift of such conditions. First, autonomous driving requires understanding the scenes by addressing multiple tasks simultaneously. However, the enormous cost in labeling these tasks make it challenging for recent large-scale datasets. Only the pioneering dataset Kitty has such labels due to its smaller scale. Second, the diversity of data is crucial for the robustness of deep learning. However, many existing driving datasets have been collected under static settings because of their easy annotation process. Some datasets are collected under adverse conditions exclusively. While helpful to domain adaptation research, they do not solve the generalization problem from its root. Finally, one of the most fascinating characteristics of the real world is its mutable nature. However, it is surprising that none of the existing datasets focus on the continuous changes through time. The very limited length of their videos make it hard to represent continuous shift in real world. For example, the shift from day to night takes hours to happen. While some datasets may be already satisfying in one of these areas, no previous dataset can be considered complete under all of these pillars. With this goal in mind, we introduce Shift, the largest synthetic driving dataset to date. Featuring 24 different domains, Shift provides more than 4,000 driving sequences collected under both static and continuously changing conditions. We now discuss our dataset design and how we attempt to fulfill the requirements. We start from the multiple task requirement. We collect data using Keller Simulator through one of the most complete sensor suites among current datasets. For each of the 6 different views, we provide a complete annotation set featuring 2D and 3D bounding boxes and instance IDs to enable tracking. We also provide optical flow, depth maps, instance, and semantic segmentation masks. Another requirement for an ideal dataset is diverse conditions. Shift provides a diverse set of conditions with different levels of domain shift. We provide fine-grained numerical domain annotation, which can be discretized into 24 coarse domains for ease of use, totaling more than 400 possible combinations of domains. With its comprehensive sensor suite and domain diversity, Shift is the first dataset to enable domain adaptation and robustness evaluation in such a large variety of vision tasks, all within the same dataset. In this video, we show a collection of different domains captured in Shift dataset, featuring variations in weather, time of day, and scenery. Finally, Shift is the first dataset of its kind to provide sequences with continuous domain shifts. We here showcase continuous domain shifts along the time of day, rain strength, and fog strength axis. Our dataset also features continuous shifts at varying lengths, and a mixture of such domain shifts. With hope of having proposed a complete dataset, we now show how our dataset is relevant for learning robust driving systems. We start from the diversity of conditions. We verify that the performance of a model trained on clear conditions increasingly drops under increasing levels of domain shifts, both under object detection and the semantic segmentation tasks. A similar trend is observed in a real-world dataset such as BDD 100K, certifying the reliability of our datasets for making observations that transfer to the real world. We hope that the continuous changes in Shift will foster research on test-time learning and adaptation. To motivate the necessity of continuous shift, we validate the performance of test-time adaptation technique, namely TANT, on domain loop closure. Using TANT, we adapt a trained model from daytime conditions to the night and then loop back to daytime. At loop closure, we observe a performance gap compared to the non-adapted baseline, highlighting the importance of continuous changes in Shift to study the catastrophic forgetting issue in test-time adaptation. Finally, we analyze the importance of providing annotations for multiple tasks to learn models robust to domain shift, a so far underexplored area. Interestingly, we find that the model trained with the most tasks is by far the most robust to severe domain shift, remarking the importance of shift to study this underexploited area. Attempting to satisfy what we view as three pillars of an ideal dataset, Shift unlocks countless new research opportunities. We hope to have sparked your interest in our dataset and the open problems it allows for solving. To find out more about Shift, check our website.